Hi everyone, welcome to the last lab for A&M 201 work through for R, and we're going to go through that lizard data that we collected in R lovingly with our beautiful lizards that were nicely brought in for us to see, and hopefully we got some good data from it as well. So you'll notice if you go into this learning materials, you'll find these two sheets. This XLS data, that was the data we collected on Tippy Downs, and I've added to it and converted it to the CSV to make it a little bit easier for you. So if you just download that, you should be able to open it up in Excel, and you can see that now we have a column with our species. And so these are all the species we had. And because we weren't able to measure mass in the lab, I've sort of just categorized them as big and small. And so this is going to allow us to answer question 3 of your report, which is how does this compare between lizards of different body masses? And then the rest of the table is as it is in your workbook. You've got footfall, subsequent footfall, stride length, stride duration, stride frequency, and speed. So that's all the data we're going to need. So I'm going to import this into R. I just have to save it somewhere. So I'm just going to save it onto my desktop so I can find it very easily. And then we can move into R. So now I have to set my working directory to be my desktop. Doing this in Windows is a little bit tricky sometimes. Doing it in a Mac is also tricky. Sometimes the desktop is a really hard place to find things, but if I just go through users, desktop, you can see it's here. So this is the right folder. I'm going to copy and paste that in and then change these slashes so they're pointing in the right direction. And that should be able to load up the right desktop, and you can see now here's a whole pile of things on my desktop which we can load in, and now we can read. I want to create a folder called dat, or I've actually called it my data in your workbook. So we'll call it my data is read.csv, which is a function, so we have round brackets, and I'm going to point it to that file, which was called lab6 underscore lizard underscore data underscore lizard underscore data dot csv. And if we do that, you can see we've loaded in 28 observations, so we had 28 lizard strides. That's a little bit low, guys. Come on, you could have done a bit better. 8 variables. Okay, so what is the question asking us to do? It says plot stride frequency versus speed and stride length versus speed. Well, we know how to do that quite well. We can just use our plot function. And if you go stride length, squiggle, speed, my data, you should get a basic plot um, of stride length and speed. You can change the type of dots. So we're going to change these to solid circles here. If you want to figure out which of these PCH codes you like the most, just Google PCH in R, super simple, and you'll get a little cheat sheet like this. You can see that these are all the different shapes we can get. So if I was to put 10 in, I would get this circle with a cross. And if I put 19 in, I get a slightly bigger circle. Let's have a quick look at that. Oh, wow, look at that. That was a big change. And so now that's our first step. So we have to plot stride frequency versus speed and stride length versus speed. And this part is missing from the lab book. Often when we do this, we want to plot them on a log-log plot. This way, when we look at the slopes, it's going to be a lot more meaningful because remember everything we looked at in class was on a log-log plot as well. So I'm going to make a variable called log stride length, and that's going to be log 10 my data $ stride length. And I'm going to do the same for stride duration and speed. So this is stride dur and this one's going to be speed, sped, lol, speed, and dur. And I've got an error here. It says non-numeric data. So that's probably because I've got the variable wrong. Yep, you can see there's a capital here and it should be lowercase. Cool, that saved it. Now I want to just plug them onto the end. So you can see I've got 8 variables. I want to add those last 3 variables here to be these 3 variables to be stuck into this my data frame so I can correlate them with this species and size a little bit later. So I'm going to go my data2, make a new data frame, is data.frame, which is a function, and my data, which is our original one. And then I'm just going to put all these after it, separated by commas. And there we go. So now my data2 is going to have those 3 ones all put together in a nice big happy family. So now we can go to our plot function again. I can point it to my data2, and now I can use the log stride length and log speed. And you can see our data is a little bit better. It now forms into a nice straight line. Some weird outliers here, but that's what happens when you use real data. Okay, so it wants us to do that for stride length and stride duration. I've gone to capital DUR. There's stride duration. It's negative. So as they get faster, the steps occur a lot quicker. Versus positive here, as they get faster, the steps are much longer. So we've done the first step, we've plotted them, and now it asks us which line has the highest slope. And by highest, we mean steepest slope. So which line is explaining more of the variation in log speed. So to do that, we can use there's a line that says something like summary fit. So what that's actually doing is 2 steps in one. So the first thing we want to do is make something called fit, which is, we could make it called anything, but I'm just going to call it fit, which is going to be the output of a fit of a linear model with stride length and speed. And if we do that, it happens. And we have something called fit, which is a linear model. And we could actually see the slope from here too. Which is nice. If we want to learn a lot more about that, we could go summary and then fit, and then that would give us a whole pile of information. We can actually combine these 2 lines into one too. Because this fit is created, I can put this summary wrapper around this. So fit gets created and then it gets used by the summary, and we should get pretty much the same output. And we do, that's nice. So the relationship's significant. It's got a moderate R squared. We're explaining about 21% of the variation. But what I'm really interested in, what the question asks, is the slope. So this one has a slope of 0.335. If we look at stride duration, or is it asking for stride frequency? So I should really have put in stride frequency here. And if we plot that now you can see we get a positive slope because the faster speeds are occurring at a higher frequency. They're taking more steps per second to get faster. But if we're interested in the slope, we can do that. And you can see here, the slope of the line is 0.81 versus 0.33 before. Now, because stride length and stride frequency, when we multiply those two, we should get speed. The sum of these two should add up to approximately 1, and you can see it more or less does. So that means we can tell how lizards are varying their speed just by looking at which one of these has the highest slope, and that's, of course, what is the point of the exercise that we're trying to do. So which has the highest slope? Question one, we will just say, well, stride length has a slope of 0.336, while stride duration has a slope of 0.812. Therefore, stride frequency has a higher slope. So lizards are predominantly changing their speed using stride frequency. Ah, that's moving on to question two. So we now have our two slopes. We've answered question one. Question two, does this lizard, or you could say all lizards, predominantly use stride length or stride frequency to modulate speed? So now we can show that these lizards are predominantly using stride frequency to modulate their speed because the slope of stride frequency is going to be higher than the slope for stride length. Okay, so that's questions one and two done. Finally, question three. So this can be question three is how does this compare to other lizards with different body masses? And so this is where we need to compare our small to large body sizes, which you can see here. I've got the size variable. Okay, so to do this, we need to make two different data sets. So I'm going to make a small data set and a large data set, which are going to be subsets of our original one. So these are going to be subsets of my data 2. My data 2 is a data frame. So if I want to take part of that data frame, I'm going to use these square brackets because remember the round brackets of a function is square brackets. So I want to take some rows from all columns of my data 2. Now, to take everything, so the format is it goes rows, comma, columns. And if I leave it blank, it's just going to take all of them. That's the default. So I'm going to leave the columns part of this blank, and I'm going to focus on the rows. Now, which rows do I want to take? Well, I want to take the ones that my data2 $size. So if we just look at this, you can see it goes big, 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 small, small, small. I only want to take the small ones, right? I don't want the big ones. So I can write a function which goes which my data2 $size equals and then small. And you can see argument which is not logical. Oh, I put the bracket in the wrong place. There we go. And so now it tells me which row numbers smalls are. So you can see it goes big, big, big for 6, and then it goes 7, 8, 9, 10. So it's giving me that. Then it's big again until we get to 15. So if I plug this into here, it's going to create a data set of only the small ones. And we could do the same for this, but this time we make this big because we called it big here. And if we do that, then we get a data set for big ones. And now we can pretty much do what we did here to look at slopes. And we can compare them instead of looking at the whole data set. We can now look at smaller data sets. So here is stride frequency, stride length, I should say, for small guys. And you'll notice the slope here is 0.64, which was different to before. And if we look at this one, the slope is 0.34. There it is here. If we do that for bigs, or large, now we see the slope is 0.51, and here it's 0.69. So the big lizards and the small lizards are changing the way that they're modulating their speed. You can see for small lizards, they're mostly using stride length because this slope is bigger. But for bigger lizards, they're mostly using stride frequency. So small lizards are getting faster by taking longer strides. Larger lizards are getting faster by taking strides more often. They're increasing their stride frequency. So there we have it. We now have a way of plotting these, um, and we have a way of comparing lizards with different body masses. Of course, the last thing we want to do is make our plots look good. So we can do a few things down here just for fun. This can be in a nice plots section. So here we've plotted stride length with speed, but we could color our species by my data $ species, um, and we can have different colors there, and we can add a legend, which is going to be, ooh, where will we put it? We'll put it down here on the bottom left. And legend equals levels there. PCH equals 19 and col equals oh, I meant bottom right, guys. There we go. So now we can see which species is which and where they plot on this line, which is a nice way of doing it. And we can do the same thing for stride frequency too, if we want. We can just change this. And we get our stride frequency. If we wanted to do that instead for body size, we could. Um, we could copy this one. And instead of having this as species, we could have it for size. And here, this would be size. And so now we have big and small lizards, and now you can start to see the separation in the slopes. So the stride length is a lot steeper for the big guys. It's a bit shallower for the small guys. And we look at stride frequency. It's the opposite. So the big guys have a much shallower slope, and the small guys have a lot steeper slope. So now we could do things like plot these lines. So the small guys are red, so I'm going to color this red. And this is actually a plot of stride frequency, so I want to do it here. And there's a line for stride frequency. You can see this outlier here is actually ruining our plot a little bit. And if we wanted to do it for here, we'd have to make it black so it matches. So this is just stride frequency and speed for large guys. And you can see here is the two different slopes that we have there. And you could repeat this for stride length as well if you wanted to make it all look pretty. Okay, guys, well, that's it for me. That's R and physiology and animal ecology for this semester. I hope to see you guys all in the lecture on Wednesday, and we can chat more then. Thanks.